Hello everyone, in this lesson we will discuss the basics of IPv6. First I will tell you about IP version 6, then in IP version 6 we will discuss routing, IPv6 address and format conversion, then we will discuss IP version 6 prefix, and finally we will finish this lesson by practicing in IP version 6. Now let's look at IP version 6 first. IP version 6 is a protocol developed against the exhaustion of IP version 4 addresses. Our IP version 6 addresses consist of a total of 128 bits and 16 bytes. As you can see here, we have 8 blocks in total. In IP version 6 we use the term block instead of octet, where we have a total of 16 bits in each of our blocks, with 8 blocks making a total of 128 bits. 1, 2, 3, 4, 5, 6, 7, 8. In IP version 4, we were separating them with a single point, and here we separate the address blocks with a colon. So why do we need IP version 6? When IPv4 was introduced in the 1990s, IP version 4 IPs were started to be distributed to all companies on the internet, but then they saw that IP version 4 addresses would be exhausted. Then they said, what should we do? These IP version 4 addresses were divided into public and private, and we should reserve the IP addresses to be used in local. Different IPs should be used in public. IP version 4 addresses using network address translate we have slowed down its exhaustion. Apart from that, ISPs have also used classless inter-domain routing to extend the life of IP version 4 addresses by dividing the IPs into subnets while distributing IPs to users, but the day will come when IP version 4 addresses will run out. Why would you say run out? Because there are billions of internet users today, so we will run out of IP version 4 addresses. So IP version 4 addresses will be replaced by IP version 6. When we look at the timeline here, you can see the development stages of IP version 4 and IP version 6. Now let's look at routing in IP version 6. IPv6 has the same processes as in IP version 4. In order to create and send IP version 6 packets on the interface, on end-user devices, these interfaces need an IP version 6 address. If the host needs to access a different subnet, it needs to know its IP on its default router. The router looks at the destination IP in the IP version 6 packet and sends the packet by matching it with the route table. Now let's look at the details of this on our next page. First, let's look at the IP version 6 header in the figure here. IPv6 header is 40 bytes in total, our source address is 16 bytes, our destination address is 16 bytes and the remaining properties are 8 bytes. In total IP version consists of 6 header 40 bytes. Here we show an example of routing in IP version 6. Let's look at the figure detailed here. The packet comes from PC1 to router 1, where the default gateway receives the packet, and if there is no problem with the Ethernet header and trailer at the beginning, it removes it and sends the packet by framing it according to the format of the interface from which it will transmit. Since leaseline is used here, it transmits the packet to router 2 by enclosing the HDLC frame, and router 1 transfers the interface to router 2 from the route table to transmit the packet, so the same operations as in IPv4 are performed in IPv6. Here, let's look at the routing protocols used in IPv6. IP version 6 uses RIP-NG, OSPF version 3, EIGRPv6, and BGP uses MPBGP4. There are no RIP, OSPF v3, EIGRPv6 and MPBGP topics within the scope of CCNA training. These topics are included in the content of CCNP Enterprise training. If you also receive CCNP Enterprise training, you can learn these topics in that training. After the shooting of this training is over, I will prepare the CCNP Enterprise training. If you take that training, we will process these topics together. Now let's look at address shortening and conversion in IPv6. IPv6 addresses consist of 8 blocks. You can see the example here. There are 8 blocks in total. We separate each block with 2 dots. Our first 3 blocks are given to ISPs as global prefix. The 4th block is divided into ISPs and given to end users. We can use the remaining 4 blocks as interface IDs, but when you get an IP from the ISP, it does not give you a prefix with 64. If it gives you 64-bit prefix, you can use the rest of it. Since there are millions of IPs, the ISP does not distribute so many IPs to you in abundance, so the ISP will give you by dividing them into prefixes according to your needs. For example, let's say they can give you an IP version 6 address with 80 prefixes, then you start over here and count 80 bits, and the first 80 bits will be your subnet ID. This is 64, when we put another 16, this is your subnet ID, and you can assign the rest to the users. In IP version 4 we used only numbers, but in IP version 6 hexadecimal values are used, that is, both letters and numbers are used. In the table here you can see the hex and binary values. In IP version 6 we use numbers from 0 to 9, letters from A to F. Each value consists of a total of 4 bits. If you remember, in the binary number system, numbers would start from the right and go to the left, and one number was twice the next number, so 2 times 1. 2 times of 2 makes 4, 2 times of 4 makes 8. The maximum value here can be a maximum of 15, the equivalent of 15 corresponds to f as hex. If you make all of the values here 1, it becomes f, where you can see the hex equivalents. For example, the equivalent of 2 is 0, 0, 1, 0. Let's write 0, 0, 1, 0, the first bit is not used, so we write 0, the value of the second bit is 2. Since there are zeros in the third and fourth bits, this is 2. Let's calculate 8, and when we calculate 8, we don't use the first bit, we don't use the second bit, we don't use the third bit, but we use the fourth bit, then this makes 8, which is 0, 0, 0. Here you can see the binary equivalence, which makes the decimal value 8. We will already discuss these in more detail in our IPv6 addressing and subnetting course. Now let's look at IPv6 abbreviations and extensions here. Here's an example of an IP version 6 address. We have 1, 2, 3, 4, 5, 6, 7, 8 blocks, and we separate these blocks with 2 dots on top of each other. Here it is written by abbreviation. Normally each block should have a total of 4 values. But as you can see here there are 3 values, here there is 1 0 in front of this value. If there are zeros in front of the IP addresses, you can write them by throwing them away, you can write them as he shows here. The block here is actually 0, 0, 12, but it is written by omitting the leading zeros. In the block here, there are 4 zeros, the beginning is written by throwing 3 zeros, in the same way that it consists of 4 zeros, and the 3 zeros at the beginning are written in this way. Let's look at the block here, again here it has a 0 in front of it, which was thrown in the same way here, 0, 0, 12, the 2 zeros at the beginning are written by throwing it, and when we look at the middle, both blocks have 4 zeros. Here they are used by combining them in this way, so here after the first 4 blocks, there are 4 zeros in the 5th and 6th blocks, and if you see 2 colons in a row here, you can understand that there are 8 zeros here. Blocks 7 and 8 already have numbers and letters, where our 5th and 6th blocks are combined. When we combine this place, we use 2 such 2 points in a row. This example below illustrates the long spelling of IPv6. Here 2001 is written as 4 zeros, 4 zeros, 4 zeros, 4 zeros, 1234 colons in a row as 56 of. If we want, we can shorten the zeros here and combine them and write them that way. So we can't put 2 colons here, 2 colons here, 2 colons here, and so on, and then 2001 and then 12, then 2 colons, and then 1234, 2 colons, 56 of. So we can't do it like here. Why can't we do it? Because in an IP version 6 address we can write twice 2 colons side by side. You can't write twice 2 colons side by side like here. Instead you can do that. Combine 4 zeros here, you write here as 2001, then you throw out the zeros here, you take out 3 of the 4 zeros here and write one of them, you can do them the same way and write 0. But while 2 colons cannot write side by side in an IP address, 2 colons can only type one next to each other. Now let's do the examples here with you. In the first example, we will shorten the IP address in a long way. Here it is also written in short, and we will write a long version of it. Let's do the first example first. We write the first block here as it is. You can't remove the trailing zeros, you can only remove the leading zeros. In the second block, we subtract 3 zeros, we write this place as 0, here we throw 2 zeros, here we write 10, here we can only subtract the beginning 0, so we can write this place as 100. Because this is 1000, you cannot throw it to the leading zeros, you have to write it as it is. We write ABCD exactly. Here you have 0101, you can throw it into the beginning 0 and write 101, you need to write the block here in the same way 1010. Now let's look at this example. In this example our first block is written exactly, our second block has no abbreviation, the third block has no abbreviation, the fourth block has no abbreviation, but there is a 0 in front of the fifth block, this is abbreviated. So we just need to put 1 0 here, all of this is okay. We can just write our IP like this way for a long time by putting a 0 in front of ABC in this block. Now let's shorten this example. We write the first 4 blocks as they are, subtracting the zeros from the 5th and 6th blocks, and writing 2 colons twice. Let's write the 7th block as it is, but we can take out the 0 in the 8th block and make it a 707. Let's look at this example. In this example 3210, twice 2 colons is given, where after 3210 you can understand that the remaining blocks are all zeros, our first block is 3210, in the remaining 7 blocks 0, 0, 0, 0, 0, I don't write them all, let me just write the first 4 blocks. All our blocks mean 0. When you shorten this address, you can shorten it here, you can shorten blocks 2, 3, and 4. Let's write this right away, 210F, let's put our first 2 points and write our 2 points on the second top to connect the blocks in between. We can write the following way, for C, 2 colons, 0, 2 colons, 0, 2 colons, D, we can't combine the zeros here, because we can only write 2 colons side by side once in an address. You can't combine the zeros here and put 2 colons side by side like this, we can only write 2 colons side by side in an IP address. You make the remaining 2 examples, friends, you can confirm by looking at the answers that there are answers to them at the end of our document. Let's talk about prefix and subnet IDs on this page. In IP version 6 we use subnet IDs as in IPv4, but here we use the term prefix instead of subnet ID. As the example here shows, you can type in 2 different ways, whether you write prefix in a contiguous way like this, or you can write it this way with a space. 64 here is our prefix, since each block has 16 bits, our first 4 blocks make it 64. 16, 16, 16, 16, or the first 4 blocks become our subnet ID. 2222, 2 colons, 1111, 2 colons, 0, 2 colons, the zeros in this block are written short, the 1 in this block also has zeros in front of it, the long spelling is 0001. This is how it is written in the subnet ID of this address, 2222, 2 colons, 1111, 2 colons, 0, 2 colons, 1, twice 2 colons, /64. So how do we find the subnet IDs? As we mentioned before, we write the prefix side in the same way below as shown here. We count the first 64 bits at the beginning, 16, 16, 16 makes 64 bits in total. Then if this is our IP address, we write down the first 64 bits of this IP address that corresponds to prefix as it is, and we write 0 in the rest of it. The prefix of this IP address is 64, combining these zeros and writing our subnet ID in this way. Now let's look at the example here, where prefix is given as 64 bits. Since prefix is 64 bits, our first 4 blocks become our subnet ID. We combine the remaining zeros and write our subnet ID in this way. Let me do some of the practices here and you do the rest. You can look at the answers at the end of our document. In this example, since it is prefix 64, we write the first 4 blocks as they are, and we write the rest in this way by combining these zeros where they are zeros. Our subnet ID here is 2, 3, 4, 0, 2 colons, 0, 2 colons, 10, 2 colons, 100, twice 2 colons, /64. Let's look at the second example, where the first block, the second block, the third block, and the fourth block make a total of 64 bits, so let's divide and write it down from here. 3, 0, A, 0, 2 colons, A, B, C, D, 2 colons, F, 1, 2, 2 colons, 3, 4, 5, 6, twice 2 colons, /64. This is how we write our subnet ID. In this example, since it is prefix 64, we divide it from here, where blocks 5 and 6 are written by combining them because they are 0, and we already combine all the remaining blocks from here and write them as follows. We divide the IP address from prefix and write the first bits as they are, we write 0 in the rest, then we find our subnet ID, we combine the zeros we write as double 2 colons. Let's look at the fourth example, where we can understand that there is 0 after the first block. From here we already have our subnet ID, and that's how we write it. 3, 2, 1, 0, double 2 colons, /64. Let's look at this example. This example of prefix is given as 64 bits again. All our examples here prefixes are given as 64 bits. Here is written as short because it is 0 after our first block. Since the last 4 blocks are reserved for hosts, we write 0 to all of them. The first 4 blocks become our subnet ID. This is how our subnet ID is written because it is combined in zeros here. 2, 1, 0, F, twice 2 colons, /64. You can do other examples. You already have answers at the end of our document. You can also look at the answers from there. Let's make a few examples to find different prefixes on this page. Let's examine this first address. Our first block makes 48. If we take it from the fourth block in 8 bits, it makes a total of 56. And when we type 0 on the remaining host side, our subnet ID is formed like here. We can write it this way. Here we can use the first 56-bit subnet ID and the rest for hosts. Let me do a few of the examples here and you do the rest. In our first example, prefix 80 is given, so let's immediately collect the bits in our blocks. Our first block is 16, our second block is 16, our third block is 16, our fourth block is 16, our fifth block is 16, and the total is 80. Then we divide our IP from here and immediately put 2 colons twice, and we find our subnet ID by typing /80. 3, 4, B, 2 colons, B, 2 colons, B, 2 colons, 0, 2 colons, 5, 5, 5, 5, twice 2 colons, /80, we can write our subnet ID like this. Now let's look at our example. In this example it gives 80 bits, then our first 5 blocks are our subnet ID. Let's write this immediately. 3, 1, 2, 4, 2 colons, 0, 2 colons, 0, 2 colons, D, E, A, D, 2 colons, C, A, F, E, twice 2 colons, /80. Block 1. Second block. Third block. The fourth block and the fifth block make a total of 80. This is how we can write our subnet ID, because this makes 80. In this example, to find 48, we need to write our first 3 blocks as they are. Let's write them immediately. 2, B, C, D, 2 colons, 0, 2 colons, 0, twice 2 colons, /48. Let me do this example. You do the remaining 3 examples. We have 40 bits here. Let's write our first 16 bits. Let's write 2, 1, 0, F in our second block. A, 2 blocks made a total of 32. Now let's look at the third block. The third block is written as 0, 0, 0, B. We will take 8 more bits from here, because the first 2 blocks made 32, and if we take 8 from here it makes 40. Then we write this way: 2, 1, 0, F, 2 colons, 0, 0, twice 2 colons, /40. We can write it this way by deleting the 2 zeros here, 210F, at /40. Since the first block is 2, 1, 0, F, our second block is A, and the first 2 values are 0 in our third block, we can write by combining them in this way. I leave the remaining 3 examples to you. At the end of our page there are already answers, and you can find them by looking from there. The basics of IPv6 are also briefly like this. We have done some practice here. We have looked at converting prefixes, and we have finished our lesson by looking at IP version 6 addresses. Goodbye, to see you in our next lesson. Hello everyone, in this lesson we will discuss IP version 6 addressing and subnetting. Let's take a look at the issues we will cover. First, I will explain the concept of global unicast addresses, then I will explain the public and private IP version 6 addresses, IP version 6 global routing prefix and global unicast IPv6 address range, and finally we will finish lesson by explaining the unique unicast addresses. Now let's first look at the global unicast address concept. We will focus on global unicast addresses in this section. As the name suggests, we call the IPs used in the real internet environment, such as the public IPs in IP version 4, as global unicast addresses. In this section we will also examine how a block of IP version 6 subnetting and global unicast addresses is created to be given to companies. Now let's look at public and private IP version 6. In IP version 6, public IPs are referred to as global unicast. Addresses that work like IP version 4 public addresses are called global unicast addresses. Companies that need IP version 6 addresses allocate IP version 6 address blocks from ISPs or global prefixes assigned to them on ISPs to end users, and these companies only use IPv6 blocks starting with this prefix. Unique local IPs are like the private IP addresses we used in IP version 4. More than one company can use the same IPs. They do not need to get an IP from anywhere. Now let's talk about IP version 6 global routing prefix. Companies that want to use IP version 6 need to get global routing prefix. Then they can distribute the global routing prefix to their users. The term global routing prefix actually refers to the idea that internet routers can have a way to express all the addresses in the address block for smaller parts of this block without the need for routes. The first company here uses prefix 2001 DB8 1111, the second company uses 2001 DB8 2222, and our third company uses prefix 2001 DB8 3333, twice 2 /64. Our internet routers here know that when they go to this prefix, they will go to router 1, so they classify IPs with global routing prefixes. Let's look at it in a little more detail on our next page. The IANA here is the entity that distributes IP version 6, where it shows that it distributes IP version 6 addresses starting with 2001 to the North American continent. It shows that it distributes IPs starting with 2, A, B, C to ISPs on the African continent. The second block is ISP 1 2001 0DB8. Then the ISP distributes them with global prefixes in the form of Company 1, Company 2, and Company 3. Let's look at the global unicast IP version 6 range. In fact, global unicast addresses use most of the space in IPv6 as well. An IP version for classes such as A, B, C, D and E are classified where the IPs are used, and in IP version 6, which IP will be used and for what purpose is categorized as follows. Global unicast addresses can start with 2 and 3. Our unique local IPs start with FD, multicast addresses start with FF, link starts with F, E, 80 in local addresses. The figure here shows how to use global unicast IP version 6 subnets. First of all, we choose the subnets we will use. We will use subnet 1 here, we will use subnet 2 here, subnet 3 here, subnet 4 here, so we choose our subnets and use a subnet between each router. Here, our first 3 blocks are global routing prefix, and our next 4th block is distributed to users by dividing it into ISP subnets. Our first 3 blocks can be used as global routing prefix, our next 4th block is subnet, and the remaining 4 blocks can be used as interface IDs. In the example here, 2001 shows 0db8, 1111, and 48 prefix, or our first 48 bits are global prefix routing, the rest is a subnet at 16 bits, and if we reserve 16 bits for a subnet, we can use 65,536 subnets. Here we can only use 65,536 subnets, or it shows the spelling of the first 16 subnets. Our first 3 blocks are global routing prefix, then our subnet ID, or it shows the first 16 subnets. Now let's look at assigning IPs to the hosts in the subnet. First we choose which subnet to use in which location. We chose to use it as 2001 db8, 1111.0001, twice 2:/64 in our location here. We will use 2 subnets here, 3 here and 4 subnets here. Our subnet here is 1, we have given 1 IP to the gigabit 0/0 interface of our router here, and we have given our host 9 IP. In the subnet here, we use 2 subnets, 2 subnets were used here, 1 interface was used here, interface 3 here, interface 2 here, and 3 subnets were used here. Now let's look at unique local addresses. Unique local unicast addresses function as private IPv6 addresses. The separation of these addresses into subnets has similarities to global unicast addresses. The biggest difference is that unique local addresses start with FD as the hex value. Unique local prefixes are not registered with any authority or company and can be used by more than one company. We can use them locally as we want. In the first 2 digits we need to use FD as hex. We need to select a global ID for 40-bit as unique. We can choose it ourselves. We need to add FD to the global ID for 48-bit prefix. We need to use the next 16 bits as the subnet space. We see that there are 64 bits left for the interface ID. The first value is 4 bits, the second value is 4 bits. We have to add the total 8-bit FD value to the beginning, then we can specify the 40-bit global ID ourselves. The first 48-bit will be our global prefix route, the next 16 bits will be the subnet ID, and the rest will be the 64-bit as the interface ID. Let's take a look at the example here. FD00, 2:0001, 2:0001, twice 2:/48 prefix was used. Our first 3 blocks were used in this way. We can also write as short as FD00, 2:1, 2:1, twice 2:/48. We can write by omitting the zeros here. This has become our unique local prefix. After determining the unique local prefix, let's determine our subnets. Here we use 1 subnet, here we use 2. Here we use 3, here we use 4 subnets and 64 prefixes, but our unique local prefix is 48 bits, our first 3 blocks are unique local prefix, and the rest we use subnets. That's all we have to do in this lesson, so goodbye to see you in our next lesson. Hello everyone, I will tell you about IPv6 address applications in this lesson. First, configure a static unicast address, then configure a full 128-bit address. Then we will finish our course by talking about EUI64 IP version 6 address format, dynamic unicast address configuration, then private address configuration in the router, and finally link local addresses. First, let's look at configuring a static unicast address. We have 2 options in IPv6 address configuration. In the first option we determine the entire 128 bits, in the second option we determine the first 64-bit prefix, and the remaining 64 bits is automatically generated from the MAC address of the interface. Now let's first look at configuring a 128-bit address. First we need to enter the IP version 6 unicast routing command in the router. If we do not enter this, IPv6 routing will not work. First here we have global unicast prefix. Our global prefix is 2001 db8 11111 twice 2:/64. Here we have 1 subnet ID, here we use 4 subnets, here we use 2 subnets. This is how we write using the IPv6 command when configuring the IP address under interface. In the interface here, it shows the long spelling, 2001, 2:0db8, 2:111, 2:0004, 2:0000, 2:0000, 2:0000, 2:0001/64. When we make them lab, you will understand them better. You can also see the IP address with the command show IP interface gigabit 0/0. Here the link points to the local address, which starts with FE80 at the local address, and the remaining 64 bits are automatically generated from the interface's MAC address. With the show IP version 6 root connect command, we can see the subnets that are directly connected on our router. Our second IP version 6 address format option is EUI64. While in EUI64 format we determine the first 64 bits ourselves, and then we automatically convert the next 64 bits from the MAC address of the interface and create it itself. So let's see how it produces it. First, the interface MAC address is divided into two. Our MAC addresses consist of 48 bits and 12 hex values. It then adds 16 bits FFFE to the middle of the MAC address it divides into two, and completes the interface ID to a total of 64 bits. Then it reverses the 7th bit of the resulting interface ID. The 7th bit makes 0, 1, and 1 makes it 0. Now let's examine this in the example on the side. We choose the first 64-bit subnet, we take the remaining 64 bits from the MAC address and create it like here, and when creating it, as you can see here, it divides the MAC address into two and adds 16 bits in the middle as FFFE, and then the 7th bit of our MAC address makes it 0 if 1, and 0 makes it 1. Now let's look at this first example. In our first example, our MAC address is 00131234 ABCD. Dividing this address, we write the first 6 values to this side and the second 6 values to this side, then we add the 16-bit FFFE hex values. After that, we change the 7th bit of our MAC address to 0 if it is 1, and to 1 if it is 0. Let's write the first 2 values here. Our first value is 0. The binary equivalent of this makes 4 zeros, as you can see here. Our second hex value is 0, and the binary equivalent of 0 is 4 zeros. Here the 7th bit translates it as 1 because it is 0, and when it translates as 1, it becomes 02. So our interface ID here will start with 0213. Now let's look at our second example. In our second example our MAC address is 1612.3456.789A. We divide this in the middle in the same way and add the FFE value to the middle. When we add 16 bits, we make a total of 64 bits, then we make 0 if our 7th bit is 1, and 0 if it is 1. Let me show the example below in 10 of them. Our first hex value is 1, the binary equivalent is like this, and the expansion of 6 is like this, 0110. This is 1, 2, 4, 8. When we put a 0 here, when we put a 1 here, when we put a 1 here, when we put a 0 here, this place makes 6, that's the binary equivalent of 6. Then if the 7th bit here is 1, we make 0, let's calculate what happens when this is 0. 1, 2, 4, and 8. Since we don't use the bits here, this becomes 4, then this becomes 14. Our interface ID continues as 1412, 2:34FF, 2:CFE, so our 7th bit here is changed to create our interface ID. This is how the EUI64 IP version 6 address format is created. On this page, let's do some practice for the EUI64 address format, where we have given our prefix as 2001 db8 11 twice 2:/64 and here we give the MAC address. To find the interface ID, we immediately divide this MAC address in half and write FFFE in the middle. 0013, 2:ABFF, 2:FEAB, 2:1001, 1, 2, 3 and 4th block. We add this intermediate FFFE to create the interface ID in EUI64 format. The first 6 values here and the last 6 values are our MAC address. This is 64-bit in total. If the 7th bit here is 0, we make 1. If it is 1, we need to make 0. We write the first value as it is. We will calculate the second value here. The binary equivalent of 0 is 0000. Since the 7th bit is 0 here, we make it 1. What happens to binary equivalent if this is 1? This is 1, this is 2, this is 4, and this is 8. Then when this is 1, this place becomes 2. And when this is 2, here is 2 out of 0. So our address is 0213. Now let's write our second example, AA13, 2:AB. From here we add FFFE in between, then we write the second half of the MAC address, AB, 2:1001. First block, second block, third block and fourth block, we added FFFE, but our work is not done yet because we need to change the 7th bit of our address to 1 if 0 and to 0 if 1. The hex value of a here is 10, let's immediately write the bin any equivalent of it, 1, 2, 4 and 8. In binary, it starts from the right and continues to the left, and if we make all the bits here 1, this will make 15, but here we will only use 8 and 2, and when we make them 0 and 0, then here it becomes 10. Since the 7th bit here is 1, we will write 0 instead, and when we type 0 here, it becomes 8 here. Then we need to write 8 instead of the A value here, or A813. I'm not doing this because the third example uses 00 because it's going to be the same as our first example, so let's do our fourth example. B80C, BE, in the middle I add FFFE, then we write the continuation of the MAC address, EFCAFE. Now here again we will convert the 7th bit to 1 if it is 0, and if it is 1 to 0. I write 1000 to find 8, here we do not write the value here because the first 3 bits are 0, because the last bit is 1, this is 8, now we make the 7th bit 1. When we make this place 1, it makes 8 plus 2 is equal to 10 here. Since this is 10, it becomes a here, and the interface ID then continues as BA0C. Let me do one more and you do the rest. Here he gave the same example of a, we have already calculated this is 8. Let's calculate this C is 0C0C, FFB, FECA, C8BA. Now we're going to translate the 7 bits here. Let's write the equivalent of CA equals 10, B equals 11, C corresponds to 12. 1, 2, 4, 8. If we make the first 2 bits 1 here, it makes 8 plus 4 is equal to 12. We write 0 for the bits here, then when they are 0, we write 1 instead of the 7th bit. When he made this place 1, he made it 8, 4, when he added 2, he made 14. D equals 13, E equals 14, F equals 15, then we need to write E instead of C. In this example, it happened this way, friends, so this is C, and this is E. In this example, we gave 8 and we had done this before, we did this and we finished our examples. Here I also wrote how you can configure it under interface, our command is IPv6 address, then we write our prefix then when we write EUI64 at the end, the ID of this interface is automatically generated. Here you can see the resulting interface ID, you can see that our local link address is the same as our IP address because our local link address is also generated from our MAC address. When you type IPv6 address DHCP under interface, it automatically receives an address from the DHCP server. On this page, let's look at the use of private addresses in routers. Routers also have IPv6 unicast routing. When we activate the router, IPv6 performs the following steps to be able to do routing. IPv6 unicast gives the interface a unicast. In the interface it allows for IPv6 routing in the direction of arrival and departure. It defines the prefixes contained in this interface, and if that interface is in the up state, it adds the prefix of that interface to the route table. Link local addresses are the addresses that we use as unicast addresses in IPv6, which are not used to stream data in IPv6 packets, but instead are used for routing by some common protocols, i.e. IPv6 link local addresses define the rules for the transmission of sent packets by any router to another subnet. As a result, IPv6 link local addresses are used for protocol messages that need to remain on our local network. For example, instead of the ARP function in IPv4, there is Neighbor Discovery Protocol in IPv6. This Neighbor Discovery Protocol uses our link local addresses. We use NDP Discovery Protocol in IPv6 to learn the MAC address from a known IP address. Our link local addresses also use this NDP protocol. These link local addresses are used in the same subnet, not to switch to a different subnet, but only to IP addresses used within the same subnet. In addition, link local addresses are used as the next hop address in routers. When we look at the example here, PC1 needs to come to the default router when it goes to PC2 here. PC1 sends the packet to the link local IP of the router with its link local IP. Router 1 forwards the packet to router 2's local link address. They use link local IPs on the back, which means that when PC1 comes to router 1, it comes with the link local address, which is used only in the same subnet. On this page, I will explain how you can configure link local addresses. We determine the first 64 bits of link local addresses ourselves, and the next 64 bits are generated from the physical MAC address. It divides our MAC address in two. The first 6 hex values are added to the left side, the second 6 values to the right side, and the FFFE is created by adding FFFE to the middle. The 7th bit of our MAC address makes 1 if it is 0, and 0 if it is 1. As shown in the example here, our link local addresses start with FE80, or our first block, second block, third block, fourth block. This is an interface ID derived from the MAC address of the interface. In the same way you can see that our IP address is generated from the MAC address. As in IP version 4, packets sent to a multicast address are delivered to all interfaces detected by the multicast address. In IP version 6, multicast addresses start with FF. Anycast addresses, like multicast addresses, the anycast address defines multiple interfaces, but there is one big difference: an anycast packet is delivered to a single address. This address is private because you can assign a single address to multiple interfaces. Now let's look at some private addresses here, like this one where when we type 8 zeros it is like putting two colons on top of each other. This address corresponds to 0.0.0.0 in IP version 4. If you see such an address, you can understand that it performs the same function as 127.0.0.1 in IPv4. This is how you can write the spelling here on a network that uses both IPv4 and IPv6. In the global unicast address range, 2000, twice 2:3. In the link local unicast address range, FE8 is 0, twice 2:10. In the multicast address range, FF0 is 0, twice 2:8. 3FFF, 2:FFFF, 22:32 are also reserved addresses for example and documentation. 2001, 0db8, twice 2:32 are also reserved for illustration and documentation. 2002, twice 2:16 is an address range used for IPv6 to IPv4 migrations. That's all we're going to tell you in this lesson, so goodbye to see you in our next lesson. Hello everyone, in this lesson I will talk about routing applications in IPv6, first IP version 6 static route, IP version 6 static default route, IP version 6 floating route, and finally NDP neighbor discovery protocol. We will finish our lesson. Now let's look at IP version 6 routes. Cisco routers follow a similar path to IP version 4 when adding IP version 6 routes to the route table, adding IPv6 addresses from interfaces that are up to the route table as local and connect, adding statically entered routes to the routing table, adding the routes learned from OSPF version 3 to the route table if OSPF version 3 is configured. As I said before, OSPF version 3 is in the content of CCNP Enterprise Training. If you also take CCNP Enterprise Training, you can learn OSPF version 3 there. Now let's look at the IP version 6 static route software here. We will already make a lab for static route configuration. I have written the commands here as an example. I recommend you to take note of these commands when you do the labs. We use the IP version 6 command, IPv6 route 2001 db8 1111 2:2. When we go to the subnet, we have specified the interface here as the output interface. Our subnet here is 2001 db8 1111 2:1. We want to go to the 2 subnet here, then we want to go to the subnet 2 in our router 1, IPv6 route 2001 db8 1111 2, twice 2:64 subnet. As next hop serial 0/0/0, we write our command in this way, in the same way that router 2 does not know one subnet and there we write one subnet. We can also check it with the show IP route static command, but this command does not work in packet tracer. When we type show IPv6 route, it lists all the routes to you. You can control the static command on the real device, making a static route using the next hop address. The only difference in this is that instead of the exit interface, we write the next hop address here. As I said, we will do them in the lab, so I pass quickly. You can also look at the commands of the applications I made in the lab from the document. Here we make a static route using the link local address, or we make a static route over the link local address by typing the link local address of our neighboring router as the next hop address. Here, static shows the default route, and when we type IPv6 route, twice 2:0, and next hop while in global mode on our routers here, we add the default route in this way. Here, I'm going to talk about floating static IP version 6 route. We did this lab before in IP version 4, and we're going to do the same lab here that we did in IP version 4. Here we have OSPF version 3 between router 1 and router 2, and here we have the backup line. We write static route on router 1 so that communication can continue when our OSPF connection between router 1 and router 2 goes. We make the administrative distance of this route 130 so that when our connection here goes, the hosts here automatically access the subnet from this connection. Let's talk about Neighbor Discovery Protocol on this page. Neighbor Discovery Protocol. It is a protocol that works like ARP and IPv4. It plays an important role on NDP routers. Let me tell you about some important functions of NDP protocol. The Neighbor MAC Discovery feature replaces ARP and IPv4. It can learn the MAC address from a known IP address. Router discovery, on the other hand, allows hosts in the same subnet to learn the IP of the IPv6 default router. It uses NDP stateless address auto-configuration messages to automatically learn IPv6 prefix information used in the host subnet. A DAD uses the DAD feature of NDP to check if anyone else is using an IPv6 address before the host uses that address. Here you can see the information we learned from NDP with the shipv6 neighbor command. Here it shows the default route discovery process. First, PC1 sends a router discovery packet to all active routers in the same subnet. The default router that receives this message forwards the link local address on the host that sends the message and responds as the default router on the network is mine. That's all we're going to tell you in this lesson. We're going to cover all of this in our labs, so you'll understand better. Goodbye to see you in our next lesson. Hello everyone, let's make IPv6 address configurations with you in this lesson. First examine a network diagram, understand our topology, then move on to our configuration. We have local area network here, we have local network here, and on the orange side, we use 2001 db8 to subnet as subnet, our IP here is 1, our IP here is 2. In the turquoise area, we use 2001 db8 subnet. The IP of our user here is 2, the IP of our interface here is 1. Here we also use for subnets between the two routers, our global prefix is 2001 db8 and our subnet ID is 4. Our IP here is 42:1, and here is 42:2. First, let's turn on our PC1, let's do the IP configuration here, then we do PC2. I come to the IP address section from the desktop, here we write our IP under IP version 6 configuration. 2001 db8 twice 2:2. Where our subnet ID is 1 and our interface ID is 2. I immediately copy it and paste it into the gateway section. The IP of our gateway is also 1. Let's not forget to write prefix here, our prefix is 64. We have given the IP of our first computer, now let's get out of here and turn on our second computer. Let's go into IP configuration from desktop and paste the IP I just copied here and edited here. Its subnet is 2. I make his IP at 2 as well. I do your prefix at 64. Let's paste it into the gateway and make it 1. Our subnet is also 2. The IP configuration of our computer here is also okay. Now let's go to router 1 and configure its IP on router 1. I switch to global mode by typing CONFT, I switch to the interface gigabit 0/1. Here we use the IPv6 address command. We did not write anything in IP version 4 before, we only wrote IP address, but here we indicate that it is IP version 6. It doesn't matter if it's a lowercase letter, even if you type a lowercase letter, iOS then converts it to uppercase letters. 1111, our subnet is 1, our IP is 1, our prefix is 64. In this way we write our address. When we press enter and say no shutdown, we configure the IP of this interface. Let's quickly switch to gigabit 0/0 and configure it. I find it from the command I wrote the old one, the subnet of this place is 4, I make the subnet 4 by shortcut right here, the IP is 1. When I enter and do no shutdown, gigabit 0/0 will also be up. Now let's go to router 2 and write our command on router 2. Let's do interface gigabit 0/0 first. Let's copy the IP address from router 1 immediately if you want. The IP of this is 42:2. I say enter, I do no shutdown. Let's configure gigabit 0 to 1 as well. The IP of this place is 22:1, this is the way it is in our IP configuration here. Now when we say no shutdown, our configuration is complete. We can check our IP configuration by typing show IPv6 interface brief. Here it shows the link local IP of gigabit 0/0 and the global unicast address that we provided. where we can see the global unicast address on gigabit 0/1. Now let's see if it pings the gateway from our computer. Ping 2001 db8 1111 twice 2:1. We have access to the gateway now. Now let's see if we can access the user from the gateway. In Windows, we ping when we type scripts, but we need to write ping IPv6 when typing in router. This is how we write the command here. The user's IP is 2001 db8 1111 twice 2:2. We have access to our user. Guys, in IPv6 this is the address configuration. In our next lab we will do static route and use this topology. We will write static route between these two routers and we will provide access to the user here from this subnet. See you in our lab. Goodbye. Hello everyone, we will make the IP6 static route configuration together with you in this lesson. First of all, let's look at a network diagram. When we look at our network diagram, it has 2001 db8 1111 subnet in the turquoise area. On the orange side, it has 2001 db8 1111 subnet. Between the two routers, we have 2001 db8 111 for subnets, and our prefixes are 64. Router 1 knows the 1 and 4 networks that are connected directly to the connect-on itself, but it does not know the 2 subnet. In the same way, the router here does not know the 1 subnet. Here we will teach router 1 to 2 subnet and router 2 to 1 subnet by writing static route. When our users here come to router 1 to go to subnet 2, router 1 will look at the route table and send us to router 2. Let's start by opening router 1 first. With the show IPv6 route command we can control our settings. As you can see, it shows the connected networks on it but does not know the 20 subnet. Let's come to global mode. On our routers, we first need to turn on the IPv6 routing service by typing the IPv6 unicast routing command. If you do not do this, IPv6 will not work in routing. Then let's write our route with the IPv6 route command. We will go to the 2001 db8 1111 subnet here, prefix is 64. Next hop address, we show the address here as our next hop address is 2001 db8 1111 for twice 2:2. You can also type the exit interface here instead of the next hop address, but it didn't work when I tried typing the output interface in Packet Tracer before. This error may be related to a problem in Packet Tracer, but normally you can also type the exit interface here instead of the IP address, but I use the next hop address. When you use the next hop address, it works more smoothly in Packet Tracer. Now I am copying the address I wrote this, friends. I will write the same command in router 2, because there I will only change these IPs. I say copy and go to router 2. Let's open the CLI. Here we need to turn on the routing feature with the IPv6 unicast routing command. I immediately paste our command here and edit on it. Our next hop address here is 42:1. The subnet we want to go to is 1. Now we have written our routes. Let's make our exit by saying end and check by typing show IPv6 route. Now we have the static route here. When users in subnet 2 want to go to subnet 1, they will go to the IP of 2001 db8 111 for twice 2:1, i.e. gigabit 0/0 interface of router 1. Let's open PC2 right away and let's put it to a test. Let's ping our user here. Let's ping the gateway first, and then we'll throw it there. We have access to our gateway. Now let's ping 12:2. Let's ping 2 subnet to 2 hosts. As you can see, our static route is working. Let's do a tracert. We will go to the subnet of 1, the IP of which is 2. Here it first goes to its gateway, and from its gateway it comes to 42:1 as a next hop address, from where it reaches the user here. Friends, you can configure static route in IPv6 in this way. Now let me show you how to write the default route in IPv6. I am now opening our default lab. In this lab, let's configure IPv6 default route. Let's take a look at our network diagram. Here we have 2001 DB8 1111 one subnet, and here we have 2 users. These users want to access the internet through router 1. We will send the requests from here to the ISP by writing IPv6 default route on router 1. The ISP has 2001 DB8 1111 8x2:8 IPs on it. I set it up by creating loopback interface 0 here. As a representation, our users here should access it. First, let's open the PC1 and test whether it can go to its gateway. Ping 2001 DB8 1111 1x2:1. We can access the gateway. Now let's see if we can access Google on the ISP. I made it 88 as a representation. We can't access it right now because there is no default route on our gateway. Let's immediately open router 1 and type the default route. Again, let's not forget to turn on the routing feature by entering the IPv6 unicast routing command. Then we write the default route in this way by typing IPv6 route in a very simple way by writing twice 2 colons and then specifying our next hop address, 2001 DB8 1111 for twice 2 colons 2. Now let's check our settings by typing show IPv6 route. Here you can see our default route. Now we can throw our ping from the user to access the internet. Now that our ping is gone, let's do a tracert. As you can see, it first goes to its gateway and accesses the ISP from its gateway and accesses the IP here. Friends, that's all we have to configure static route and default route. So goodbye, see you in our next lesson.